Hello, Math 1730 students. This is Jeff Parent coming to you live from the studios at A203, the Royal Oak campus, WMTH, the station that rocks the docks and reaches the beaches. Hopefully you're having a good break. Wanted to help you out with section 4.3. 4.3 discusses increasing and decreasing functions. So let's talk about that. In fact, we're going to start with the mean value theorem, kind of a little reminder. The mean value theorem says that if you have a continuous function over some interval, say a to b, that there's some point in that interval where the slope of the tangent line equals the slope of the secant line. So those two would give you parallel lines there. Now let's apply that to our current topic, increasing and decreasing functions. So we'll start with an increasing function. Increasing functions are what they look like, are what they're supposed to be, that as you move left to right, the function's getting taller. Now what's that mean for us in terms of calculus? Well, I'm glad you asked. The mean value theorem says, and here I've restated the mean value theorem in terms of x2 and x1. The mean value theorem says that there's some point, here, so that the slope of the secant line equals the slope of the tangent line. Now where it exactly is doesn't really matter. What I want to do is I want to examine this quotient. So in the numerator of that quotient, we've got f of x2 minus f of x1. Now for an increasing function like this, that numerator is really going to be the difference in these y values. So f of x2 minus f of x1, not much we can say about it other than the fact that it's positive. Now likewise in the denominator, x2 minus x1, since x2 is to the right of x1, what's the sign of the denominator going to have to be? Bonus points, positive. Now if I have a positive divided by a positive, well, overall that quotient's going to be positive. And what that's saying is that if the derivative of a function is positive in some interval, the function has to be increasing in that interval. And that's the major conclusion we wanted to get at this. That's one of the big things we get out of the mean value theorem. There'll be another one when we do the fundamental theorem of calculus. So what's that look like for decreasing functions? Well, I'm glad you asked. Let's move down here to decreasing functions. So that quotient, f prime of c equals f of x2 minus f of x1 over x2 minus x1, is still going to be positive in the denominator. You're still going to do right minus left for a decreasing function, and you're still going to get something positive. However, when we do the numerator, f of x2 minus f of x1, you're going to get something, yes, negative. So what kind of a quotient do you get when you divide a positive by, a negative by a positive? Well, you get a negative quotient. So this gives us an easy means by which we can discuss and see the behavior of a function. If on some interval, say a to b, f prime of x is greater than 0, then f of x is increasing on that interval. And similarly, if f prime of x is less than 0, then f of x is decreasing. And that's the major conclusion out of this first little bit here, is that based on the sign of the derivative, you can tell what a function's doing. You don't even have to look at the graph. You don't have to know or understand what the function is. You can tell if it's increasing or decreasing just by looking at the sign of the derivative. Now we've got a lot of examples, and they're going to be increasing in difficulty and show you a range of tricks. But let's start out with kind of a friendlier example, just to kind of get your feet wet on this. It's going to be problem number 26. That's 28. Let's try 26. Okay. Now in all of these things, you have to consider what the domain of your function is. Now in the case of a nice polynomial function, the domain is everything. So negative infinity to infinity. There's no place that you can get a 0 in the denominator, a negative under square root, or the negative of a log. Sometimes I'll write that as script r. Now f prime, you should be able to calculate pretty easily. That's 3x squared minus 12x plus 0, which we'll leave aside. And I want to know where this function is positive or negative. So first of all, let's figure out where it's actually equal to 0. So setting this equal to 0, I can factor out a 3x, that leaves behind x minus 4. And that gives me 2 points. 2 places where this function can actually equal 0. You have something times something else equals 0. Either 3x could equal 0 or x minus 4 could equal 0. And that gives me 2 places where this graph crosses the x-axis. 2 places where it's actually equal to 0. And let's write those down right here. 0 and 4. I've got a nice little chart that I'm going to fill in here. So at 0 and 4, the derivative is 0. We're going to ignore this part of the chart over here. I don't need that extra little space. But what I want to see is what's happening on either side of these points. So what's happening to the derivative to the left of 0? What's happening to the derivative between 0 and 4? What's happening to the sign of the derivative to the right of 4? Well, I need to come up with some test points. So let's remind ourselves that f prime of x is 3x squared minus 12x. And let's pick a point to the left of 0, say f prime of negative 1. So it's going to be 3 times negative 1 squared minus 12 times negative 1. 3 plus 12 is 15. Now it doesn't matter that if I get 15 or 15 million. The point is that it's positive. And what that tells us is that the function is increasing. Okay, that's cool. How about between 0 and 4? Well, let's choose a value and test it. That value has to be between 0 and 4, so maybe 2. So let's test f prime of 2. F prime of 2 is going to be 3 times 2 squared minus 12 times 2. So 4 times that's 12 minus 24 is minus 12. And again, the big thing to see here is the sign of that function. It's negative. And if the function is negative, that's telling you that the function is decreasing in this interval. Let's keep going. One last point to test. I need something to the right of 4. I'm going to test that in the derivative. So say 5. 3 times 5 squared. 5 squared is 25. Times 3 is 75. 12 times 5 is 60. So, okay. The important thing to see is not that you get 15 exactly, is that you get something positive. And again, that reflects that you have a function that's increasing there. So what have we learned? Well, we've got a function that's increasing on this interval. Everything up to 0. So from negative infinity to 0. Parenthesis. Where else is it increasing? Well, to the right of 4, the function's increasing. So 4 to infinity. It's increasing there. Okay. How about decreasing? Where is it decreasing? Well, it's decreasing between 0 and 4. So, kind of nailed it. That's what's happening to our function. you can look at it graphically and see this kind of behavior that we predicted from here. So let's do that. You can do this on your graphing calculator. I happen to have it already printed out for us. So to the left of the y-axis, that is between negative infinity and 0, right up to there, the function is increasing. Then what? Well, between 0 and 4, the function's decreasing. And then it changes. You have a point where the derivative is 0, that is, you have a horizontal tangent right there at x equals 4, and at that point the function starts climbing again. So the function's increasing from 4 out to infinity. So there's your intervals. From negative infinity to 0, from 0 to 4, and from 4 to infinity. Increasing, decreasing, increasing. Let's continue. Problem number 28. Now I said at the start of this that there's going to be kind of an increase in difficulty and tricks. 28 starts that little increase. First of all, this is another polynomial function, so its domain is just everything. So we'll write down negative infinity to infinity. Places where you have holes in the domain would include places where the denominator is 0 or the root has a negative underneath. You have to throw out such points. But in this case, we get our script r as before. Now in terms of finding the derivative, the first thing you have to do is use the product rule. So f prime of x, let's call this kind of like the f of x, and that's a g of x. You have to differentiate the outside with the chain rule. 2 times x plus 2 to the first power times the derivative of the inside. So that's your f prime times g plus g prime. So what's the derivative of x minus 1? Bonus points for saying 1 times f. Let's clean that up a little bit. What you should notice is that there's a greatest common factor between the x plus 2's here. In fact, I'm going to take out that GCF, x plus 2. It's going to leave behind a 2, well that's gone, times 1, times this, x minus 1, plus, and I've taken out one of these, so that'd be just x plus 2 to the first power, which is left behind. Let's keep going. Inside the brackets here, x plus 2 times, well, that's 2x minus 2 plus x plus 2. And I get some nice, helpful cancellation here. Inside the brackets, I'm just left with 3x. 3x plus 0, let's just call it 3x. Now, as before, we're interested in trying to find where this is actually going to change signs, where it could change signs. And it can change signs at x equal negative 2 and x equals 0. So those are the 2 points. In fact, there are critical points in this particular problem. The points where a function can change sign may not always be critical points, but it will include the critical points, if there are any. So again, let's put these down here, negative 2 and 0. We'll ignore this third column here. Won't need that. And let's see what's happening to the derivative between these points. Is it positive? Is it negative? Well, soon enough, we're going to turn to our graphing calculator and do these things on our graphing calculator. But for this first one, I think we can kind of do this one in our head. I need a point for f prime of x, f prime of x. Let's see, let's distribute that. That's going to be 3x squared plus 6x. So f prime of, say, negative 3, that's going to be 27 minus 18, so that would be 9. And even if I made a mistake in here, What I did make a mistake on is that the derivative is positive. Now, if the derivative is positive, what's that tell you about the function? Kudos to those of you who said increasing. Let's keep going. We need to test a point between -2 and 0. Now you could choose -0.16735, etc., or something crazy like that. But I like to apply the KISS principle, which is keep it simple. So applying the KISS principle, let's just type in a -1 or test a -1 here. So 3 times -1 squared plus 6 is, 6 times -1 is going to be -3. And again, the point is not the exact value, but the sign of that value, which tells you that the function is decreasing. Last but not least, f prime of, say, well, let's keep it easy, 1, tells us that the function is increasing to the right of 0. So kind of the same thing as the last one, increasing, decreasing, increasing. So those intervals, when I ask you this kind of a problem on a test, those intervals would be from increasing on -infinity to -2, and from 0 to infinity, and decreasing on -2 to 0. Once again, you can see that by the graph. So -infinity to -2, and from 0, I know that it crosses the x-axis at 1, but it doesn't start it starts increasing at 0. And then finally, between -2 and 0, the function is decreasing, so as it goes down to its minimum. Let's keep going. Now, the first few examples that we've tried have been nice polynomial examples. Let's try something that's a little bit more challenging. Problem number 16. Now, this is something that I emphasize a lot because it's easy to make a mistake on this. Sine squared of x. Start by writing it as sine of x quantity squared, because as you differentiate this, you need to use a chain rule. F prime of x is going to be 2 times the sine of x, so that's the derivative of the outside, times the derivative of the inside, which is cosine of x, plus the derivative of sine of x again, which is another cosine of x. Oops, my bad. What did I forget here? I forgot the domain. Sine of x is defined everywhere, -infinity to infinity. Script R. Okay, so we need to find where this is actually equal to 0. So finding where it equals 0 will help us out, because then we can find where it's positive and negative by testing points in between. So if I set this equal to 0, my suggestion to you would be to factor this out and solve. Now, there's a greatest common factor of a cosine of x. So let's factor that out. That's going to leave behind 2 sine of x plus 1. And I want to know where that's equal to 0. I've got a product of two things that's equal to 0. So I can set each one of these equal to 0 and solve. Let's start with the cosine of x. In fact, maybe you know where cosine of x equals 0. What coordinate is cosine on the unit circle? Okay, I should hear a chorus of pi over 2 and 3 pi over 2. Hopefully that was your voice in there as well. So cosine of x equals 0 when x is pi over 2 or 3 pi over 2. In fact, more generally, and I gave extra credit on the test for this, pi over 2 plus n pi. Now for the other possibility, 2 sine of x plus 1 equals 0. That's 2 sine of x equals negative 1. So sine of x equals negative 1/2. I'm going to have to leave you on your own to work this out. You get sine inverse of negative 1/2 on your calculator would give you negative 30 degrees, which is also positive 330 degrees, or 11 pi over 6. There's another angle for which that works as well, and that other angle would be a little bit past, be right here. So you've got 30 degrees here and 30 degrees here. So 180 plus 30 degrees is 210 degrees, and that's 7 pi over 6. So, wow, got a lot of points here. We've got 1, 2, 3, 4, and that's just in the interval 0 to 2 pi. All right, well, let's put these down in order. So we'll start with pi over 2. Next comes 7 pi over 6, and then 3 pi over 2, and finally 11 pi over 6. Now this is where it gets a little tricky. We need to test the sign of the derivative in all these intervals. It might help you out to come up with some numerical values. So this is approximately 1.57. 7 pi over 6 is approximately 3.66. 3 pi over 2 is approximately 4.71. And let me show you the last one. All I'm doing is just taking and plugging these into my calculator. So 11 second pi divided by 6. So about 5.76, for instance. So let's put that one down as well. So about 5.76. And let's put that function into our calculator, and we want to put in the derivative, not the function, because we're testing the derivative. And we can use test points based on numbers that are between these. So let me enter that into my calculator. I've got a few other functions that are there. I shut off their graph by pressing the equals, or putting the cursor on the equals key and then pressing enter. So I want sine of x, right parenthesis again, squared. Whoops, no, I want the derivative there, not the function. My bad. 2 sine of x, right parenthesis, cosine of x, another right parenthesis, plus cosine of x, another right parenthesis. So when I do a table, it's going to show up as y4. All these other ones are shut off. Second, and then the graph key gets us to the table. Now let's figure out what values we're going to test. So I need values that are between these. Something to the left of 1.57 is 0. Something between these could be a 2, and then say a 4, and a 5, and a 6. So let's see what happens when we test these out. So you should have your calculator set up with table set. So second table set, that should be set to ask. That way you can type in whatever values that you want for your t-table. So let's type in 0, 2, 4, 5, 6. What you should notice is not the exact numbers, but is the sign of those numbers. Positive, negative, positive, negative, positive. They alternate. You had 4 points, that gives you 5 intervals. So positive, negative, positive, negative, positive. So the function is increasing, decreasing, increasing, decreasing, and then increasing. Now let's think about what's going to happen, what kind of a point this is going to be if a function is increasing, going up and up and up and up and up, and then all of a sudden you get a place where the derivative is 0. And what does it mean that the derivative is 0? The derivative of 0 means that you've got a horizontal tangent there. In fact, that happens at all these points. But if the function's increasing, maxes out, and then starts decreasing, then this is a local maximum. Might be a global maximum, but that's a little different. We have to figure that out. Now, on the other side of things, if something's decreasing and then starts increasing, what does this have to be? A local minimum. And then another local max, and then a local min. Now let's see if this matches our expectations. So let's look at the graph here. And here you go. From 0 to pi over 2, so along this interval in the x-axis, the function's increasing. Once we get to pi over 2, from pi over 2 to 7 pi over 6, the function's decreasing. And then there's this little interval from 7 pi over 6 to 3 pi over 2 where the function is increasing again. Let me see if I can't make that a little bit easier to see. There we go. So from 7 pi over 6 to 3 pi over 2, it's increasing, then decreasing, 3 pi over 2 to 11 pi over 6, and finally from 11 pi over 6 to past 2 pi, but generally we're going to look at from 0 to 2 pi, it's increasing again. So beautiful. There's problem 16. Now the one thing that you can't do with a video is ask questions. But what you can do is if you have questions, you can write them down and get them answered at the start of class or before class with the SI sessions. Let's try problem number 40. I've kind of cheated on problem number 40 a little bit. I've already given you the first derivative. But what I haven't discussed is the domain. Now you should know that there's a problem here. X can't equal -1. Thing is, even though -1 is not in the domain, it can't be a critical point. It is a place where the function can change sign. So we're going to have to list that down below when we look at our table. Now the derivative, you have to use a quotient rule to get that, can be factored in the numerator as x plus 3 times x minus 1. In looking at the derivative, this can change signs where the numerator equals 0. So that's, well, that'd be -3 and +1. So there you go, -3 and +1. But remember, it could also change signs where the denominator equals 0. So even though the denominator is not part of, the value -1 is not part of the domain, the function can still change signs there. So let's see about this. Okay, so I have to enter that one into my calculator. And there it is. It's the first one there. Let me shut off the bottom one of these. So go down here, press enter. Let's get rid of that. And then we'll go to our table. Let me delete all the old values from our previous problem that are still there. I need test points between these things to find out where the derivative is positive and negative. So some good test points would be, I don't know, let's not be too adventurous, -4. If I want to keep the integer values, there's not much choice there, or here. And just for giggles, let's put 17 here. It doesn't really matter as long as it's to the right of x equal 1. Now what we're looking for is the signs there. So let's type in those values. -4, -2, 0, and 17. Now I could have equally well put 17 million, and oh my, they're all positive. Wow, that's kind of a surprising result here. I hope the graph bears that out. But let's take a look at this. That would tell me that it's positive, positive, positive. You know, that can't be right. Something has to be wrong here. What is it? Oh, what's wrong is I put in the function, not the derivative. So, bad on me. Let's shut that off. Let's come down here. You know what? I think I can just modify that. X squared, it'd be plus 2x minus 3. And now let's look back at our table. So, positive, negative, negative, positive. So kind of a strange pattern there. A little bit unlike the alternating patterns we've seen before. Positive, negative, negative, and positive. So what's it telling us about the function? Well, increasing, decreasing, decreasing, and increasing. Let's go back and actually see the graph of the function and kind of confirm that it matches our expectations here. So plugging in the original function, not the derivative, we want to graph the original function. So x squared minus 2x plus 4 divided by x plus 1 squared. Let's set up our window, say between -4 and 6 on the x-axis. And I'm just going to take a guess at -5 to 5 on the y-axis. Let's see what we get. So one of the things you could expect is a vertical asymptote. And indeed we got that. Half of our graph seems to be wasted. So let me adjust this a little bit. I'm going to make y minimum say -0.5 because I don't think we need much below the x-axis. Y maximum, let's make 6, and let's go a little further down on the negative x-axis. You're not going to have to be experts in graphing these things on your graphing calculator. So what's happening here? Well, the function is increasing until it gets to our vertical asymptote at -1. And that's what we see on the graph. It's increasing from -infinity to -3. Then what? Actually, the function keeps increasing, doesn't it? There's something wrong. Let's back up a second. My bad. I put the function in wrong. This isn't squared. That's to the first power. I might need to readjust the window. Let's go down to, say, -5 again. Okay, so we're seeing part of the behavior. I'm going to zoom out a little bit on the graph. Window, -20 to 20. See if that captures more of the behavior. Perfect. So the function's increasing to the left of -3. And then once it gets to -3, which is right here, then it starts decreasing. So increasing from -infinity to -3. And where else? Well, starting at 1, right here, the function bottoms out and starts increasing. So it's increasing from 1 to infinity, and then decreasing from, well, starts decreasing at -3 to infinity. No, -3 to, my bad, to -1. And once you cross that vertical asymptote, the function is still decreasing. It decreases from -1 to 1. All right, so my apologies for a few of the miscues on that one, but I'm hoping that overall you still got the gist of this. The important thing here is to consider the domain, and the domain led to a point where the function could change signs. One last one here, and it's kind of a look ahead to section 4.4. It's problem number 22. Now there's a couple ways you could do problem number 22. Let's first think about the domain. You can't have a 0 in the denominator. In fact, this number has to be greater than 0, and it can't even equal 0. It can't equal 0 because that would put a 0 in the denominator. It has to be greater than 0 because you have a square root there. So the domain is 0 to infinity. Now there's two ways you can approach trying to find the derivative here. And let me discuss them both. The first is to use the quotient rule. So here's the quotient rule. Square the denominator times the derivative of the numerator. The derivative of the numerator, the derivative of the denominator times the numerator. When you distribute that, you end up with like terms. This and this are like terms. So I've got one of them here, 1/2 here. 1 minus 1/2 gives me 1/2 x to the 1/2. Minus, this is still hanging around, 3/2 x to the minus 1/2. Now this is an important trick here. The half and this, the smaller of these exponents, so you got two fractional exponents, the smaller one's going to get factored out. So when I factor that out, that gives me 1/2 x to the minus 1/2 times x minus 3. And we'll go over this in class. But let's do it a different way here, and maybe I'll spend a little more time on that. The other way to work this is to divide both of these by the denominator. So I get x over x to the 1/2 plus 3 over x to the 1/2. Now if I subtract exponents, 1 minus 1/2, I get x to the half. 3 over x to the 1/2, I can write it like that. And now finding the derivative, this isn't the derivative yet. Finding the derivative is going to be a lot easier. I don't have to use the quotient rule. I don't have to combine like terms. So it's going to be 1/2 x to the minus 1/2, negative 1/2 times 3, it'd be a negative 3/2 x to the minus 3/2. Okay. Now what? Well, kind of like our previous work here, you're going to factor out the greatest common factor, and you're going to include the smallest negative exponent. So that would be a 1/2 and x to the negative 3/2. Now, as a reminder, when you factor something out like this, each of these terms get divided by that factor. So each term is going to be divided by 1/2 x to the minus 3/2. 1/2 x to the minus 3/2. So this is going to get divided by 1/2 x to the minus 3/2. And this is going to get divided by 1/2 x to the minus 3/2. Now this is a lot of tricky algebra to deal with, which is what's great about having this thing recorded. You can go back and replay it. But these things cancel each other out. And when you divide a fraction by a fraction, the trick is to invert and multiply. So I'll multiply by the reciprocal of 1/2. The 2's cancel each other out, and I get a 3. So I'll get something minus 3. Now, how about over here? Well, again, some nice cancellation. This time, the 1/2's cancel. But what's going to happen with the exponents? When you divide things with the same exponent or same base, you subtract their exponents. So a double negative means it's a positive. I end up with x to the first power. Go double check me on that. Finally, the 2 is in the denominator. This can come to the denominator, and I get x minus 3 over 2x to the 3/2. So where can this equal 0? Where is it undefined? Well, it's undefined at 0. But 0 is really kind of on the edge of our domain, so we don't really have to worry about that. It can actually equal 0 where the numerator is 0. So at x equals 3. So let's test that and call it a day. So let's just clear out this top function here and put in our derivative. So it's x minus 3 divided by parentheses 2x raised to the 3/2. Let's be easy about this. 3/2 is 1.5. Exit the exponent with a right arrow like that. And let's go do our table. I got a lot of errors here, so that's because of my old values. Let's go back. Remember, the domain is 0 to infinity. So there's nothing to the left of 0. I don't have to test anything there. I have to test 2 points. I have to test something here between 0 and 3, and something to the right of 3, say a 5. So those are the 2 points that I'm going to test. Let's delete those, our old values, and test a 1 and a 5. So negative and then positive. So negative, positive, decreasing and increasing. What kind of a point must 3 be? Is it going to be a minimum or a maximum? All right. And I heard a big chorus of minimums. So let's give a hand for those of you who said minimum.
That was easy.
Yay, good job. And let's see if I can find the graph. There we go. Right there. So there's the graph. You have your vertical asymptote at 0, which is why it's undefined there. Comes down to a minimum at this point of 3, and then it starts increasing. So decreasing, then increasing. For homework, try 1 through 17, 21 through 39, and I'm going to get really choosy from here on out. So 45 and 57 through 63. So I skipped a lot of problems in here. I want to keep this light for you so that you'll work on it and get something good out of it. Okay, good luck.